Hi there, everybody. In this video, we're going to be talking about homogeneous linear differential equations of second order. So we're actually going to be looking at two derivatives instead of just one. So what is a second order linear differential equation? It's an equation of this form, right? We're going to have two derivatives of y plus some function of x times y prime plus some function of x times y equals some function of x. If you can write into this form, it's a second order linear differential equation. Now, these don't need to be functions of x. I mean, y might be a function of t, in which case you'd see t's here. Or it might be a function of some other variable, r or s, in which case you'd see r's or s's here. All right? But we're using x in what we're talking about. So one thing I want to talk about is just a quick example. Okay? So let's just look at a quick example. One very simple but very useful differential equation of this form is the following one: y double prime equals a constant. Okay, so this differential equation is very useful for describing. This is exactly how we describe the motion of a falling object. All right, if I drop my pen, right, the only force that's affecting it is the force of gravity, and we know that gravity causes things to fall at a constant acceleration of negative 9.8 meters per second squared. That's the only thing governing the motion of this pen. Let's ignore things like air resistance and breezes and things like that. Suppose we're just in a vacuum, all right? Gravity is the only thing affecting this, and so it falls at a constant acceleration. And so that's exactly what this differential equation is saying. This differential equation is saying that the acceleration, so now I'm thinking of this as a function of time, so t will be my variable here, is a constant. And notice that this is a differential equation of this form. Y double prime, well, p and q are just 0, and f of x is just a constant, right? So it is of this form, right? So you can actually solve this differential equation pretty easily. This one is particularly easy to solve. You just anti-differentiate both sides, right? So if I anti-differentiate both sides, I'm going to get y prime equals at plus some constant b. And if I anti-differentiate again, I get y equals 1/2 at squared plus bt plus c. Now, if I propose this as an initial value problem, if I said that at time 0, y was h0. So this is my initial height, right? At time 0, y might describe my height, and it's saying that it's just some fixed number. So put whatever number you want here that would describe the height of the pen at the beginning. And then I might also indicate the initial velocity, y prime of 0. I'll call that v0. So that would be the idea that I would be imparting some sort of initial velocity on the pen before I release it. So I might shove it downwards, I might push it as I release it, or I might throw it up, right? If I throw it up into the air, I'm imparting an initial velocity, right? So that's what that would be describing. Okay, so if we impose these initial conditions, we can see what happens down here. Well, that will allow us to determine these constants. So if I go down to this equation and use this, well, this is saying that when t is 0, y prime is v0. So this thing becomes v0 equals a times 0 plus b. In other words, b is equal to v0. Right, so we figured out what the constant b was. And this one, I can use this equation to simplify this one. This is saying that when t is 0, y is h0. So if I plug that one in, I get h0 equals 1/2 a times 0 squared plus b times 0 plus c. Well, this stuff's all 0, so this is just saying c is equal to h0, the initial height. And so I can rewrite this again. Y is equal to 1/2 at squared plus v0t plus h0. And this, if you're familiar with basic physics, this should look very familiar to you. This is exactly the formula we use to describe the height of a falling object that is undergoing acceleration a with initial velocity v0 and at initial height h0. And so this is exactly the thing that governs the motion of falling objects. And so that's a pretty cool thing, cool application of this, of differential equations. Now, one thing I want to do is I want to look at a pictorial representation of this. So let's draw some axes here. I'm going to have my t-axis here and my y-axis here. And let's just see what we're doing here. When we say y of 0 equals h0, that means that the value of y when t is 0 has some initial height here, h0. And then when we say y prime of 0 equals v0, well, y prime is the slope of the graph of y. So we're specifying not only the initial point that the graph has to pass through, but we're also designating its slope, right? So we're saying that the slope is equal to v0. And if we investigate this expression a little bit more closely, we see it's a quadratic, and so we know it graphs as a parabola. Typically, if we're dealing with gravity, a will be negative, pointing downwards, right? Because gravity pulls downwards. And so we know that this parabola opens downwards. And so I should get a curve that looks like this. And this is exactly the type of trajectory we expect to see when we throw an object, right? It follows a parabolic trajectory. Now, keep in mind, this is actually time, it's not position. So this is actually modeling something that could be thrown directly up and falling directly down, right? It's just that as I extend it over time, it makes a parabola. But the reality of the situation might be just something going directly up and falling directly back down, all right? But over time, it makes a parabola. Of course, this is the same shape you would get if you threw it with a little bit of horizontal velocity. It would also follow a parabolic trajectory like this. But this differential equation is only talking about the vertical component of its motion. Okay, so that's just an application of second-order differential equations. What are we going to be looking at in this chapter? We're actually going to be looking at the homogeneous type. So a differential equation is called homogeneous if the right-hand side is 0, is identically 0. So 0 for all x. That's what this triple equals means. It means it's 0 for every value of x. And so we're really going to be focusing on differential equations of this form, which admittedly, this one is not, right? This is not 0, but I think this is a good example to kind of get a feel for what's about to happen here. So we're going to be focusing on these type of differential equations. And in particular, we're going to be looking at the initial value problem, okay? So we're going to be studying exactly this kind of thing, right? Where we specify a point and a slope. And we hope to be able to produce the solution given that information. Contrast this to first-order differential equations where we only needed one initial condition. For second order, we're going to need two. Okay? So the initial value problem dictates that we need two initial conditions. And typically, you'll see one is for just y at a point, at a value of x, and then the other one is y prime at a value of x. However, there are other ways to set this up. You don't need to do y and y prime, but that's a traditional way to set this up. Okay, so one cool property of these linear homogeneous equations is the following thing that I'll just propose as a claim. Okay, so if we happen to find solutions, and I'm going to call them y1 and y2, all right? If we happen to find solutions y1 and y2, and we take any constants, c1 and c2, then I claim that this right here, this is called a linear combination. Any linear combination of y1 and y2, so c1 y1 plus c2 y2, is also a solution. Okay, and that's going to be a useful fact for us. So if we can find two solutions, we can take a linear combination of them and get a new solution. Now, why is that true? Well, let's look at the proof of this fact. Okay? How would we prove this? Well, I just need to show that this really is a solution, right? So I'm going to take this and I'm going to plug it into the differential equation, and we should get 0. Okay? So let's see what happens when we do that. So the proof. I took this and I plugged it in place of y, right? So there it is in place of y, just on the left-hand side. Now, what's that equal to? Well, to simplify this, what I'm going to do is I'm going to focus on these derivatives. And what I'm going to do is I'm going to distribute these derivatives through. We know that derivatives work that way, right, across a sum. So we distribute those derivatives through, right? And so we come to here, right? The next thing we're going to do is we're going to take a look at these coefficients, p of x and q of x, and we're going to distribute those through, right? When in doubt, just expand everything out. Get rid of these parentheses. That's essentially what we're doing. Okay, so now we got this stuff, right? Got rid of those parentheses. Now what can we do next? Well, what we're going to do is we're going to focus on the y1s, what I have in blue, and the y2s, which I have in red. All right? Let's group those together. All right? Well, we'll just rearrange terms. Okay, so I got the y1s over here, and the y... Oh, I'm missing a derivative here. Okay, so this should be a second... I thought I fixed this on the slide. Look, this should be a second derivative. This should be a first derivative. Okay? Hopefully that fixes in a second. Then what I'm going to do is I'm going to pull out these constants. I'm going to factor out the constants, right? So, oh good, I fixed the derivatives. They're back. See, that should have been a second derivative here and here, and a first derivative here and here. But I got them right down here. Okay? But I pulled out the constant, C1 and C2. Now, what can we do here? Well, now, remember what we started with, a hypothesis. Our hypothesis was that y1 and y2 are solutions. Okay? That means that if I plug y1 into this differential equation, it makes it true. So that means that this thing with a y1 in place of y is equal to 0. And that's exactly what I have here. In blue, that thing is going to become 0. Similarly, if I plug y2 into this differential equation, I get 0. So what's in red here is going to be 0. So I get this. And so C1 times 0 plus C2 times 0 is 0. So what have we shown? We showed that when you plug this in to the differential equation, we get 0, which means that it is a solution. So we proved this claim. Okay? And take any two solutions, any linear combination, didn't matter what constants these are, any linear combination of those solutions is also a solution. Okay. All right, so the next thing we need to talk about is when we can expect solutions to exist. If I give you a set of initial value conditions, do we actually expect to be able to find a solution? And is that solution going to be unique? In other words, could there be more than one solution given a set of initial conditions? All right, so and if you think about that throwing the pen into the air example, or a ball into the air, you know, if I start at initial height and initial velocity, are there two possible things that could happen, or only one? Right? So we have a theorem for this. So let's take a look at that. It's theorem 5.1.1 from your book, and it starts with a hypothesis. Suppose P and Q are continuous on an open interval, AB. Okay? So let's just get a picture of what's going on here. So we have some open interval, A to B, right? Some open interval. And these functions are continuous on that open interval. It says x0 is any point in AB. Okay. And let k0 and k1 be any real numbers. Okay, not sure what those are doing yet. But when I look down at the initial value problem, I see, oh, okay. See, they're saying y of x0 is k0. So the height of the graph above x0 is k0. So this is the point x0, k0. So we're insisting through the initial value conditions that the solution go through this point. But we're also insisting that its derivative be equal to k1. So the slope of the tangent line to the solution is equal to k1. Okay? So what does the theorem say? Well, it says that this initial value problem has a unique solution on the interval. So that means that we can expect to find a solution that does go through this point and has that tangent line, and it exists for all x in between a and b. Okay, so I just drew one possibility of what it might look like here. And it says it's unique, which means that from this point you can't have two different solutions coming out. There's only one. So this is the unique solution. So this is an important theorem for us. It's going to tell us that, in fact, when I throw that pen into the air with some initial velocity and initial height, there's really only one thing it can do. Now, that's actually a little bit different. The theorem doesn't really apply to that situation because, remember, that wasn't a homogeneous differential equation, but that's an analogous situation to think about. Okay, so the differential equation we're going to look at here is this one. Okay, and I'm going to put along with this two initial value problems. All right, so initial value problems. First, I'm going to look at the initial value condition that says that y of 1 equals 2 and y prime of 1 equals 0. The next one we're going to look at is that y of negative 1 equals 2 and y prime of negative 1 equals 0. Now, what's the picture here? Well, y of 1 equals 2 means we're going through this point, right? And y prime of 1 equals 0 means we have a horizontal tangent line. What about, so that's initial value problem 1. What about initial value problem 2? It's saying that y of negative 1 is 2, so we're going to go through this point, and y prime of negative 1 equals 0. So we're going to have this slope for our tangent line. So that's initial value problem 2. So we're going to solve both of these separately, okay? Now, before we do this, I want to take a look at this and compare this to what our theorem says. Now, if you look at our theorem, so our theorem, notice what it says. It's talking about a differential equation of this form, okay? It's talking about a differential equation where the leading coefficient is just a 1, right? Now, that's not what we have here. We have an x squared, okay? So we need to do something about that. We need to get it into this form before this theorem applies. So the first thing we should do if we want to talk about how the theorem is going to relate to this is we should get this into the form that it has. So we're going to divide through by x squared. All right, so if you divide through everything by x squared, we get this. Okay, so now we are of the form that the theorem specifies. Now, what does the theorem say? It says, suppose P and Q are continuous on an open interval, AB. Well, what are P and Q here? Well, this guy is our P of x, and this guy is our Q of x. Where are they continuous? Well, they are continuous everywhere except 0, right? Because with 0, these things aren't defined. But otherwise, they're rational functions that are continuous everywhere else. So the theorem will guarantee a unique solution on any interval on which both of these are continuous. What that means is that we can't include 0 in our interval. So if I'm dealing with initial value problem 1, the intervals that I can use can't go past 0. Right? They can go up to 0, but they can't go past it because they can't include 0, right? So my intervals can go anywhere from 0 off to the right. Right? So the theorem is going to guarantee a unique solution provided we restrict ourselves to the interval from 0 to infinity. That's for initial value problem 1. For initial value problem 2, we have the same issue. We can't go past 0. We have to include our initial condition, of course, but we can't go past 0. So we can go up to 0, but not beyond. So we're going to have this region. So for initial value problem 2, we can only guarantee a unique solution from negative infinity to 0. That's what the theorem is telling us. Okay? So what I'm going to do is I'm going to give you two functions, and I'd like you to verify that they're solutions. Okay? So verify that these guys are solutions to the differential equation here, not the initial value problem. All right, they're not going to actually work. You could check that too. That would be a good exercise. Verify that they're not going to satisfy this, right? But they are solutions to this. Okay, so well then wait a minute. So if they're not solutions to the initial value problem, then is this hopeless? Well, it turns out no. There's something we can do with these. Okay, so pause the video, verify that these solve the differential equation, okay? And now what we're going to do is we're going to remember what we talked about at the beginning of this class, and what we talked about was this claim. This claim says that if we have two solutions, then any linear combination of them is also a solution. Aha, so let's try using that. All right, so once you've verified that these are solutions, what we're going to do is we're going to then we know from the claim that this thing is also a solution for any constant C1 and C2. So let's see if we can find the constant C1 and C2 that satisfy the initial value conditions, right? So if we look at initial value problem 1, it says y of 1 equals 2 and y prime of 1 equals 0. Well, we're going to need y prime, right? So let's compute that. So we're going to have 2c1x minus 2c2x to the negative 3. Okay? Oops. Off the camera there. Now, the condition that y of 1 equals 2 is going to tell us that, so this is for initial value problem 1, right? It says that 2 is equal to what we get when we plug in 1 here. So that's C1 plus C2. And initial value, and the other part says that y prime of 1 is 0. So if I plug that stuff in here, I get 0 equals 2C1 minus 2C2. Okay, so this is a system of two equations and two unknowns. So pause the video, solve this system for C1 and C2. Find out what they are. Okay? So what you should have found was that C1 and C2 are both equal to 1. Okay? So we can get this to solve the initial value problem if we take these to be our values for our constants. And the theorem says that we have a unique solution on the open intervals 0 to infinity. So what we're conclaiming is that y equals x squared plus x to the negative 2, I plugged in 1 for C1 and C2, is the unique solution on the interval 0 to infinity. And this is the unique solution to the initial value problem 1. Okay? Now what about initial value problem 2? IVP 2. Well, here we had y of negative 1 is 2 and y prime of negative 1 is 0. Okay? Well, let's plug that stuff in. Okay? So y of negative 1 is 2. So that gives me this, just like before. And y prime of negative 1 is 0. Well, that means y prime is 0. If I plug negative 1 in here, I get negative 2c1 plus 2c2. So solve this system of equations. Go ahead and do that on your own. And you should have gotten, again, c1 equals c2 equals 1. And so y equals x squared plus x to the negative 2 is the unique solution to IVP2 on the interval negative infinity to 0. Remember, we're not guaranteed that it's unique for all values of x, only where those functions were continuous, so only on this interval. Okay, let's go take a look at a picture of what's going on. Okay, so what we're looking at here, you can see the blue curve is the curve that satisfies the differential equation for the initial value problem 1. It goes to the point 1, 2, and has a horizontal tangent line there, right? So that solves the initial value problem. Now, you can ask, well, what about the red part? Well, the red curve can be lots of different things and still solve the differential equation, right? Now, the position of the red curve has nothing to do with the initial value problem because the initial value problem is talking about this point. So you can see there's lots of different solutions. I can move this red curve around and get lots of solutions, which means the solutions aren't unique. So you can see that the solutions aren't unique if we allow ourselves to look at all non-zero x. We only have a unique solution determined by the initial condition if we restrict ourselves to x greater than 0. Okay? And so that's why we specified that interval 0 to infinity, and vice versa for the red one. So the red one was the solution to the second initial value problem, but the blue curve could be lots of different curves that satisfy the differential equation. And so this part of the graph is not uniquely determined by the initial value condition. So we only get a unique solution if we restrict ourselves from negative infinity up to 0. So if you're looking for a unique solution, you have to be careful to keep your eyes out for where P and Q are continuous. Okay, so there's more to talk about in this section. This is just the first video, and we'll get to the other stuff in the next one. So I'll see you there. Okay.